Welcome to Chapter 3, home of all of the molarity calculations. This chapter is considered by pupils of A-level chemistry to be one of the hardest parts that they have to overcome. But it's foundational in that we're going to need to use all the skills we pick up from this chapter in everything else we do. So strap in, this is going to be a bumpy ride. What if we were interested in how much of something we had? Well, up to now, whenever we were quantifying how much of something there was, we would perhaps measure the mass in grams, or alternatively, we could figure out how big it is, like measure the volume in decimeters cubed. But chemistry works different to this. Chemistry works based on individual particles colliding with other particles, rather than mass or volume, so it would be sensible to define an amount of substance relative to the number of particles. Enter into our story Avogadro's number, named after Amedeo Avogadro, but not a number that he came up with. Amedeo, who had more children than he knew what to do with, he was a chemist, Italian chemist in the late 1700s and early 1800s. He proposed that two gases at the same temperature and pressure would always contain the same number of particles. Later, we determined exactly how many these were at standard room temperature and pressure for carbon-12. We based it upon carbon-12 because we had to base it upon something. Carbon is really important in all organic chemistry, in you and me, and is not at either extreme of the periodic table, neither being too small or too low mass element or too high mass element to start behaving strangely. It was very, very well understood. And because it was well understood, what we could do is we could define Avogadro's number relative to the amount of atoms in 12 grams of carbon-12. It was once said that the average mole weighs 12 grams and the average mole is made predominantly of carbon. But I don't believe this at all. You see, if 12 grams contains 6.02 times 10 to the 23 atoms, we would describe that as 1 mole of substance. It means that 1 mole of any substance contains the same amount of atoms as 12 grams of carbon-12. Why this strange and obscure comparison? Well, we have to compare it to something. The Celsius scale is compared to the freezing and boiling points of water. And, we have to compare this to something tangible and measurable. And carbon-12 was something that we could measure in a straightforward way. And there we have it. 1 mole is always 6.02 times 10 to the 23 atoms, no matter what the substance. Why 12 grams, I hear you ask? Well, convenience. Because if you look at the periodic table contains two numbers. The atomic number, which is which element it is in the sequence, and also how many protons or how much positive charge its nucleus has, and also how many electrons a neutral atom is going to contain. But the second number, the interesting number, is the atomic mass, or the relative atomic mass. It's the number at the bottom of this, of each of the tiles in this periodic table. Oxygen, for example, is approximately 16, and nitrogen approximately 14. Now, because those numbers are what they are, carbon is 12. If we pick 12 grams of carbon-12, later on it's going to be really convenient because it's going to scale with the relative atomic mass. You're going to see that in action a little bit later. But it basically means that 1 mole of nitrogen is going to contain 14 grams, which is the same as its relative atomic mass in AMU. So it's very, very convenient. Let's see some examples, and you'll believe me then. Take a look at argon. Argon is that noble gas, and it's right up there, just underneath neon in group 0, on the far right-hand side of the periodic table. Now, it has a molar mass of 40 grams, and that means that 1 mole of argon would have a mass of 40 grams. It means that 40 grams of argon would contain 1 Avogadro's number of atoms, 6.02 times 10 to the 23. Now, whenever we're describing this molar mass as taken from the periodic table, we give it a capital M and then follow it within brackets, the symbol of the chemical we are talking about. The molar mass of uranium being right down at the very bottom of the periodic table, M brackets U is equal to 236 grams. So the mass of 1 mole might increase down the periodic table, but actually the number of particles that are in that mole remains exactly the same. Now, if I got a mole of multiple different substances, like in this picture here, they might fill up different volumes, but this is down to the density of those substances. It has nothing to do with the number of particles. There's not more particles in the one that's more voluminous. That's to do with how close together the particles are packed. Trust me, 1 mole contains 1 Avogadro's number of atoms. Did I really just say atoms? Well, it's not always atoms, because sometimes it's molecules too. You see here, I have an oxygen molecule made of 2 oxygens bonded together. Now, I might be interested in the number of particles. Here, the molecule acts as a particle. So the mass of each particle isn't the mass of a single oxygen atom, but is the mass of both oxygen atoms combined. It means that the mass of O2 is 16 grams plus 16 grams. That's equal to 32 grams. And in the same way, the molar mass of water is the mass of a hydrogen and another hydrogen and an oxygen. 1 plus 16, and that's equal to 18. Now's the time to have some fun, because you're going to have to do this an awful lot in chemistry, either going from a named compound and writing down its formula, or alternatively being given a molecular formula for something, and then being able to write down what its molar mass is. So if we just look at a single one of these, H2O2, what is the molar mass of H2O2, hydrogen peroxide? Well, the 2 hydrogens are going to be 1 each, and the 2 oxygens are going to be 16 each. So what's that? 34 grams. You just need to add up their individual masses, as displayed on the periodic table. And so here it is, what I believe is to be one of the most important formula in all of chemistry. It's a formula that is used in nearly every single reaction and every time you prepare a chemical. It's the formula that gives you the number of moles. And what we must do is take the mass of the sample, what we've found on the weighing scales, for example, and divide it by that molar mass that we took from the periodic table. That would give us the number of moles. Now we're going to use this, so you need to make sure that you know how. Chapter 13 contains 12 distinct different calculations, and nearly all of them use this formula at some part. So get used to it. And there's no better way to get used to it than just having a go at some questions. Here, this is just using that 3-variable relationship and rearranging it to give you the missing variable that you might need. And the answers are presented here. And what's this? More questions? Well, you're only going to get good at this by practicing again and again and again. And again and again.